Howdy! In this video, we're going to discuss minimum spanning tree using greedy algorithms. Alright, so what is the minimum spanning tree problem? The minimum spanning tree problem is basically a problem where we are trying to find the minimum cost of connecting the graph. So, for example, if we have a graph like this, we basically want the minimum cost of connecting all of the vertices of the graph. So one example of a spanning tree could be a tree like this where we are using this edge, this one, this edge and this edge. So this is connecting all the vertices, but the cost of connecting the tree, which is basically the sum of all of the edges in this case, is 13. Whereas if we connect the edges, these two edges, and then if we use this edge, and this edge, we end up with a minimum spanning tree like this, where the cost of building this is basically equal to 7, where 7 is the sum of all these edges. So 3 plus 2 plus 1 plus 1, which gives you 7. And so we are trying to make the minimum spanning trees like this from a given graph containing edges and vertices. Alright, so there are basically two main algorithms to find the minimum spanning tree. The first one is the Prim's algorithm, and the second one is Kruskal's algorithm. Note that both of these are examples of greedy algorithms, which means that both of these are greedy. Alright, so let us understand some basic facts about MSTs. MST over here means minimum spanning tree. So a minimum spanning tree basically satisfies the following three conditions. The first one is that every vertex is connected with edges so that you can reach one vertex from any other. So you could basically reach any vertex from this vertice, and similarly you can reach every vertex from this vertice and so on. And then we basically use v minus 1 edges with the smallest edge weights. So one thing to note over here is that the number of edges in the minimum spanning tree is always going to be v minus 1. And there are no cycles in the minimum spanning tree, because if there is a cycle, it's not going to be a tree anymore. Alright, so let us try to understand Prim's algorithm first. So the main idea of the Prim's algorithm is that we are trying to compute a minimum spanning tree in successive stages, where in each stage we pick one node as the root, and then we basically add an edge and thus an associated vertex, and then we'll keep adding the minimum edge. So we'll keep using the greedy choice until we finally get the minimum spanning tree. So basically the input for a Prim's algorithm is a source node where you want to start from, and the graph, which consists of the vertices and the edges, and then the output is basically a minimum spanning tree. Okay, so let us look at an example of Prim's algorithm. So for example, if we have a graph like this which has 5 vertices A, B, C, D and E, and multiple edges, then in order to use Prim's algorithm, we'll just consider that our starting node is A, but you could also start with any other vertex, and you should get a minimum spanning tree which has the same cost. So minimum spanning trees might not be unique, but the cost of the minimum spanning tree always is unique. Alright, so we'll start with edge A over here, and so we basically get that the distance from edge A to edge A is 0, because it's the same edge, and then it doesn't have a parent, so the parent is just a hyphen, it's blank, and then we basically pop the vertex A, and now we see that the vertex B has a distance of 5 from A, which is the minimum distance we have seen until now. So we write the distance of B is 5 and the parent is A. The distance of C is 3 from A. So the distance of C is 3 from A, and similarly the distance of E is 2 from A. So we get that the distance of E is 2 from A. And now we pick the minimum edge, which in this case is edge from A to E, because the other edges are of length 3 and 5, which are greater than 2. And so we basically pop the vertex E, and now we see that there's a edge from E to B, which is again of length 5, but we won't change the original distance from 5 because we already have a similar edge, so there's no purpose or there's no use of doing that. And then we also find that there is an edge from E to D of edge weight 3. So now we'll add that to the table. So we have um, the distance between E to D is 3 and the parent is of course E. And now we'll find the minimum one from these three, and so we get the minimum one is again vertex C. So we pop the vertex C and then we again update the distances. So the distance from C to B is 4, which is less than 5, so we'll update the distance to HB now. And similarly the distance from C to D is 1, which is again less than the previously seen distance, so we'll update that also. And that's how we get the distance from D to C is 1 and the parent is C. And now we'll again find the minimum distance vertex, which is D in this case because it is at a distance of 1 from the vertex C. And so we'll pop D now, and again for D there's nothing more to be done because we have already discovered all of the other edges which it is connected to. And so note that after we pop A, we just don't need to consider the edges to and from A. And similarly after we pop E, we won't worry about the edges or edge distances to E. And similarly for C, and now for D. And then finally we'll pop B, and so that's how we get our minimum spanning tree. And so our minimum spanning tree basically consists of the edges from A to C, A to E, B to C, and C to D. So if you count the number of edges, we have 1, 2, 3, and 4 edges, which is V minus 1, because V over here is 5, and that's basically how the Prim's algorithm works. So let us discuss the running time of Prim's algorithm now. So basically the running times of the Prim's and Dijkstra's algorithms are the same. The performance of Prim's algorithm depends on a graph representation and the implementation of the minimum priority queue. So using binary heaps we can basically do the extract minimum operation in logarithmic time. So yeah, so here's an example of a pseudocode for Prim's algorithm. So basically what we do is we initialize Q with all the vertices from V, and then for each U belongs to Q, we'll initialize the distance to that vertex as infinity and the parent of that vertex to be nil. And then for the source node, which in our case was A because we started from A, we will define the distance or the weight to that node to be 0, and then the parent of that node is nil because there's no parent for that node. And then we have A equals to null, and then so A is basically like sort of a cloud of the currently discovered vertices. And then while Q is not empty, we will extract the minimum from Q. So U is basically the minimum edge we find, and then if U is not equal to S, we'll say A equals to A union of the cloud. So we'll add this edge to the cloud of vertices we have already found, and then we have a for loop which checks all the vertices which are adjacent to you, and then it will update it if um, they are like at a distance less than the currently seen distance. And so the running time for this for loop over here is big O of v, and then the while loop runs v times, and then the extract minimum operation takes logarithmic time, and so the time complexity of this function basically, or this operation basically, comes out to be v times O of log v because it's v times. And then this if statement is again done v times, and the for loop over here, it's very interesting to note over here that the for loop basically runs e times, where e is the number of edges, because if you think about it, that no matter how many times you look into like vertices, like this for loop basically is independent of the number of vertices, because it's always going to run only for e number of times, where e is the number of edges. And so we basically get that the update operation again could go up to e times, and so that's basically how we get the running time to be v plus e times log v, where v log v comes from here and then the e log v comes from this operation right here. Alright, so that's it for Prim's algorithm. Now let's look into Kruskal's algorithm. So basically the idea over here is that you basically try to select the edges in order of smallest weight and accept any edge which does not cause a cycle. So the input in this case is just the graph, and the output is the minimum spanning tree. Alright, so let's do Kruskal's algorithm to find the MST of this graph again. So we first sort the edges by weight. So we had all of these edges over here, and then we'll sort them by their weights. So we changed all of these so that they are now in increasing order of their weights. And now we'll call make set on each of these vertices. So we first call make set on each of the vertices from A, B, C, D, and E. So we have 5 different sets now. And now for each edge E in the vector, we'll call find set on the vertices the edge connects. And if the two sets are different, we'll call union of the two sets to unite them. So for example, we first go to the first edge, which is C to D of length 1. So we're talking about this edge right now. And so when we do find set of C, we find that the find set of C is just C, and for find set D we get that the find set of D is again just D. And just because they are not the same, we'll call union to join these two sets. And so when we call union, we get that these two now become one like cluster, one big cluster of two vertices. Alright, so let's move to the next edge now. So the next edge is from A to E, which is of length 2, and we basically find set of A, which is just A, and find set of E gives us just E again. And as they are not the same, we'll call union on these two sets, and so we get another cluster AE. Alright, so let's now jump to look at the third edge. So the third edge is from vertex A to vertex C of length 3. And so when we do find set on A, we get that the find set of A is basically AE, and then the find set of C is CD, and as these two are not same, we'll again union them. So when we union them, we get AECD as one big cluster. And now we'll jump onto the fourth edge. So the fourth edge basically consists of two vertices D and E of length 3. So we're talking about this edge right here. And when we do find set D and find set E, we'll get that they both are in the same set. So as they are the same set, we don't need to union that, because that would basically be redundant. And so we'll move on to the next edge now without unioning. So the next edge is from vertex B to vertex C of length 4. And so this edge right here, and so find set of B gives us just B, and then the find set of C is basically AECD. This is a typo, I'll fix it later. But so as they are not the same, we'll call union on these two sets. And so when we call the union, we again get AECDB. And so now we finally have a minimum spanning tree, but we'll move on to the next edge. So for next edge, vertices A and B of length 5, we see that find set A and find set B are the same. So we'll again just ignore it and move on to the next edge. And so for the next edge, we again find that the find set of B is AECDB, and the find set of E is again the same thing. And so again we will just ignore it and then move on to the next edge. But over here we are finally done with all the edges, and so yay, we get the minimum spanning tree. Alright, let's try to understand the running time of Kruskal's algorithm. So for Kruskal's algorithm, what we did is for every vertex we first make a set of V, and then we basically sort all the edges of E in increasing order of their weight, and then we'll check every edge E in sorted order, and then if the find set of U is not equal to find set of V, we'll add that edge to the set A and then union the vertices U and V. So as you can see, the for loop for making set of each vertice takes big O of V times, because it runs V times, and make set is a constant time operation. And then sorting all the edges takes big O of E log E time, which can also be written as E log V square, because the maximum number of edges for a graph can be basically V times V minus 1 over 2, right? So you can also write it as big O of E log V square, and this again simplifies to 2 times E log V, which is just big O of E log V. And then this for loop right here runs E times, because there are E edges in the sorted vector or like list, and then we'll basically find set U and find set V, which again the union operation over here will take V minus 1 times of big O of log V, because we know that find set will not be equal to find set V V minus 1 times. And then we finally return A, which is the minimum spanning tree. And thus we get the running time of Kruskal's algorithm is again big O of V plus E log V, where we get E log V from here on simplifying this, as I just mentioned, and we get V log V from over here, where V minus 1 times of O of log V can be written as V log V. And so yeah, that's about it for minimum spanning trees. I hope this was helpful, and good luck for your exams. Thank you.